So far we've been talking about walks, paths, and cycles in ordinary, undirected graphs. Now let's move to digraphs. Digraphs are often more useful when you model networks and things like that, so it makes sense to once in a while talk about them and see how they work. So what is a walk in a digraph? Well, it's exactly the same thing. It is called a directed walk because digraphs want to be fancy and have this name directed all over the place, but it's the same thing. It is a finite sequence of edges that now are called arcs because we're in a fancy digraph of the same form. Each edge ends where the next begins. So, for example, if you have a digraph like this, say, so I have X, Y, Z, and W, then I can walk from X to Y. Now, really, the order is important. From Y, I can go to Z. I cannot go to W because this is the edge WY. It goes in the wrong direction. So I cannot drive against traffic. So I have to go from Y and Z, and then I can stop there, or I can go from Z to W, and so on. So that is a walk, a directed walk in a digraph. And alternatively, you write it with arrows. You call V0 the initial vertex, Vm the final vertex, and the length of the walk is the number of steps. Exactly as in regular graphs, you can define directed trails, directed paths, and directed cycles. So let's look at an example. Of course, when I say exactly, I mean you have to beware of the fact that now you have arrows, your edges are directed. So if you look at this graph, then X, Y, Y, X, this is a trail. So remember, trail meant that you do not repeat the same edge twice. And indeed here you are not, because there is one edge going from X to Y and a different edge going from Y to X. Whereas if you would go XY, YX, and then XY again, now you're repeating the edge XY twice, so this is not a trail. Only the first one is a trail, and so on. Using paths and knowing what paths are in directed graph, we are now sufficiently mature to ask the question, what does it mean for a digraph to be connected? So let's go back a bit and forget digraphs and look at regular, undirected graphs. Regular is a bad word because it actually means something, but ordinary graphs, undirected graphs. There, the definition was that your graph cannot be written as a union of two pieces. But we also showed a bit later that another way to see this is that you're saying that between any two different vertices, there exists a path. And we showed that these two things are equivalent. Well, for digraphs, they are not the same thing. They are not equivalent. Let's see how this works. So we are going to call a digraph connected if it cannot be expressed as a union of two digraphs. And we're going to call a digraph strongly connected if you had the second condition, namely there is a directed path between any two distinct vertices. Why are these not the same, did I tell you? Well, look at these examples. Let's look at this graph. This digraph is not connected. And it's not strongly connected either. First of all, because it's the union of X and the graph with Y, Z, and the edge between them. That's why it's not connected. It's not strongly connected because there is no directed path between X and either of Y and Z. Now look at the following graph. This graph is connected because it is not the union of anything. It's not in two separate pieces, but it is not strongly connected. Because all paths lead into y. I can't go, for example, from x to z. Think about this as a city. If you lived in a city where you had these two roads, and they were one-way roads directed like this would be a disaster. All cars will end up in y for all eternity. So the graph is not strongly connected. You do not have a path in any direction you want between any two vertices you want. There is no path from x to z. There is no path from y to anywhere. Whereas, for example, this graph is strongly connected. Because if I want to go, it's a roundabout, so I can always go around as many times as I want until I get to where I want to get. So another way to see this is that the graph being connected, namely it cannot be expressed as a union, this is something that has nothing to do with the directions of the arrows. This is the same as saying that the underlying graph is connected. So the underlying graph is connected means that there is a path, not necessarily respecting the directions, between any distinct vertices. So if we go back to these examples, this example here, I mean, you can drive from x to z. You just have to break the law when you drive from y to z. So if you only are worried about graphs and not about paths and not respecting the direction, then this graph is connected. So being connected, a digraph being connected, means that there is a path not necessarily respecting the directions. Being strongly connected means that there is a path that also respects the directions. So that's why strongly connected actually is stronger than connected, so the name is good. But so strongly connected implies connected, but not the other way around. With this, now we can ask a further question. So suppose I start with a graph. Not a digraph, just a graph. And I ask the following question. Is there a way for me to put arrows on the edges so that the digraph that I create becomes strongly connected? In this case, I can, right? So I told you that if I do it this way, but assume that we had another graph, like this graph. So I have a cycle here and a cycle here. Now, will I be able to put arrows in a way that will make this graph, the digraph I get, strongly connected? No, because look at this bridge. If I make this bridge one way from left to right, nobody who lives here will be able to drive here. If I make it one way the other way around, I will have the opposite problem. So I have to orient this bridge in some way, and whichever way I do it will prevent the digraph from being strongly connected. So this is something that is not always the case, and therefore it's interesting to study. So we call a graph orientable if you can direct the edges in such a way that the resulting digraph is strongly connected. And any such digraph will be called an orientation of G. Of course, any graph that is disconnected automatically fails, because if it's not connected, it will never be strongly connected. So this is why the assumption of connectedness is not necessary. It will be automatic. So when is a graph orientable? It is orientable if and only if each edge lies in a cycle. So remember, this was our problem here, that this edge did not lie in a cycle, and therefore the graph was not orientable. So let's prove this. So assume that there is an edge that does not lie in a cycle. So you have the same problem we had with the bridge, we have here u, v. So I have to orient it in some way, and if I orient it from u to v, then I cannot go back from v to u along this edge. And then, since this doesn't lie in a cycle, there is no other path. If there were another path that I could possibly take back, then this would be inside a cycle. Since it doesn't lie a cycle, I cannot do this. So it's necessary that each edge lies in a cycle. But I need to prove if and only if, so I need to prove that assuming that each edge lies in a cycle, I do get a connected graph that is orientable. Well, assume that each edge lies in a cycle. Let's try to produce an orientation of our graph to show that it is orientable. So you pick a cycle. If each edge lies in a cycle, well, I mean, you have the trivial case if there are no edges at all, but then there is nothing to prove. So you assume that there is at least an edge. Then you know that there exists a cycle that this edge has to lie in by assumption. So you have this cycle, and the cycle is very easy to orient in a way that makes it strongly connected. You just orient it cyclically, meaning you make all the orientations consistent with each other, so you go round, 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 and then you can go from any vertex to any other vertex. Okay, so if you have a cycle, you orient it cyclically. Maybe you also have another edge. Then you can orient this edge in any way you want. Both ways will give you a digraph that's strongly connected, because you already have a nice road here. So there might be several ways to make a graph oriented. That's not a problem. So if you have a cycle, you orient the edges cyclically, then you look at your graph. Did I cover all the vertices? So if all the vertices of your graph were in this cycle that you just oriented, then you're done. As I said, you can orient any other edge whichever way you want, and you're done. You have no more vertices that you need to care about, that you need to reach from one vertex to another. So then we're done. If not, then there is an edge that is not in C, but adjacent to C. So why is that? Well, your graph is connected, right? So if your graph looked like that, and this was not all vertices, you have some other vertex, but then you have an edge that goes to that vertex. Let's color this edge in a different color. There. But then this edge lies in a cycle because we're assuming each edge lies in a cycle. So you trace that cycle and you orient its own edges cyclically, except the ones that are already in the blue part. What have we now created? Now, the original vertices in the blue cycle, these could all reach each other, so that part of the graph was strongly connected. If you look at this vertex, well, you can always go back to the blue graph, circle around, and go out from it again. So every red vertex, from every red vertex you can go to the blue cycle, and you can reach every red vertex from the blue cycle. So the red and blue vertices together form a strongly connected graph. In other words, your edge lies in a cycle by assumption. If you orient the edges of this cycle cyclically, except those that are already in your original cycle, then any vertex in the new cycle can be joined by a path to the old cycle and by a path from the old cycle. So the graph that you have formed so far is strongly connected because any vertex from any vertex your path will go to the blue cycle, circle around as many times as you need, and go out from it again to the vertex you want to reach. Now you ask yourself, does this cover all vertices? If yes, you're done. If not, repeat. You take a new edge, it will lie in a new cycle, and so on. You trace that cycle, you orient it, You go on until you have covered all vertices. Since you are in a finite graph, this will end. So now you will have a strongly connected graph. Some superfluous edges you might not have needed to orient, you just orient them any way you want, and you are done. So this proves that a connected graph is orientable if and only if each edge lies in a cycle.